Hey there. As promised, let's go through a very simple example of the different types of equilibria that systems can experience. So one example would be the example of balls rolling on a set of hills. Here on the x-axis, we might have the state of the system, which would be the x-coordinate in the case of the balls. On the y-axis, we have what we could refer to as a potential. In the case of the balls, it's actually a potential energy. So you could imagine a situation where a ball is balanced precariously on the tip top of a hill, and if you don't move that ball, it will stay there. So it's not changing its position in time. It is at an equilibrium, but this is an unstable equilibrium because as soon as you roll the ball to one side or another, it's going to go to a completely different state, either this x position or this x position. So the balls at the bottom of the hill are at stable equilibria, because if they're perturbed, if you move this one over here, for instance, or over here, it's just going to roll back to the valley again. And so those are stable equilibria. Another example might be a penny that is balanced precariously on its side. You might think of this as having high potential because there is a part of the penny that's relatively high above the table. But as you might expect, this is an unstable equilibrium, because as soon as you tilt the penny a little bit, it's going to just topple to the table and go to its stable equilibrium point, which would be flat on the table. So we could just annotate this as another unstable equilibrium. So if you're ever trying to evaluate the nature of an equilibrium, just think about what happens as you move it a very small distance away from that equilibrium state. And it's key to think about moving it only a small distance away, because if you were to displace this ball over here to this side of the hill, for instance, it wouldn't return to its original position. It would converge on this other stable equilibrium. And so whenever you're evaluating stability, it's important just to think about how it's going to respond to small perturbations around that equilibrium state. I've been throwing around this word perturbation, but it's not one that I've officially defined yet. A perturbation is a temporary disturbance. Some examples of perturbations might be the impact of a volcano eruption on climate. When Mount Pinatubo erupted in 1991, it caused 1 degree of global cooling until 1993. So this was a temporary disturbance that went away after those 2 years, after all those ash particles eventually rained out of the atmosphere. Another example of a temporary perturbation in biology might be the effect of a windstorm on forest biology. So windstorms tend to topple large trees and open up parts of the canopy that were previously closed, which enables a lot of pioneer species to come in. But after several years, those pioneer species are replaced by the species that succeed them, and eventually you rebuild the former canopy structure that was there before. So that windstorm would be a temporary disturbance, in other words, a perturbation. We could contrast perturbations with forcings, which are more persistent disturbances. So one forcing that you might not be aware of is that our sun is actually continually getting brighter. It's been increasing in luminosity or brightness over the last 4.5 billion years. It increases at a slow rate. It's not something that we have to worry about. It's only 5% every billion years for our sun. Other suns increase in luminosity at different rates. So if you're ever feeling down, you could go to bed with the comfort that the next day will indeed be a brighter day. Other types of forcing that are present in Earth systems are the continuously increasing CO2 levels thanks to our relentless burning of fossil fuels, and also continual urbanization. So in this part of the lecture, we're going to take some of these concepts and vocabulary words and apply them to understand how a system can become self-regulating. And we're going to use the example of Daisy World. It's kind of a cartoonish example, but it's actually the very example that led James Lovelock to propose the Gaia hypothesis, which we'll talk a little bit more about at the end of this lecture. But this Daisy World example was something that a group of very high-powered scientists actually learned a lot from and inspired a lot of thinking in both Earth system science and the more general science of complex systems. So the basic premise behind Daisy World is that it's a planet that only consists of two entities. There's dark soil and then white daisies. So remember that white surfaces have high albedo, they reflect sunlight, whereas dark soil absorbs sunlight and has very low albedo. Daisy cover in Daisy World depends on temperature. Like most plants, there's a temperature optimum at which daisies are happiest. And you might think that Daisy World would converge to a happy, stable equilibrium with everything peaceful except one thing. The sun is getting stronger, so there's a continual increase in luminosity. And the question that we're going to attack in this thought experiment is whether Daisy World is going to fry or stay cool. So we can actually plot this increase in luminosity over time. So this plot shows you what happens to suns in general over time. So on the x-axis here, notice we have age, and then on the y-axis we have a ratio of these quantities, luminosity, radius, and temperature, with respect to the current sun. So in the present day and age, all of these have a ratio of 1, because everything is normalized by the present. But you'll see that luminosity is increasing over time. It has been fairly linear at this rate of 5% every billion years, but as the sun gets older and older, that rate will eventually increase. The radius of the sun also tends to increase over time. It follows a similar trend as luminosity. And the temperature of the sun, in contrast, tends to stay relatively flat. But as the sun gets older and older and becomes larger and larger, it will eventually also become cooler. But scientifically speaking, how does the surface temperature of our planet, Daisy World, change as the sun's luminosity increases? So you can think of Daisy World as being a very simple representation of an actual Earth system. So let's view Daisy World as a two-component system, where the two things that we're interested in are the coverage, or the area of this planet's surface that daisies occupy, and the surface temperature. And we need to develop some couplings between them. So we know that surface temperature impacts daisy cover. I've already told you that there's a happy optimum at which daisies are most abundant. But then there's also a coupling from daisy cover to surface temperature through albedo. So that's a fairly straightforward coupling. We know that as daisies increase, they have very high albedo, so the albedo of this planet is also going to increase, and surface temperature is going to go down. So an increase in daisy coverage leads to a decrease in surface temperature, and so we have to represent this as a negative coupling, just as so. But how about the coupling in the opposite direction? Okay, what's the impact of surface temperature on daisy coverage? This is a little bit more complicated. I'm going to leave this as a question mark right now, because if we're below the optimum temperature for daisy growth, an increase in temperature will lead to an increase in daisy coverage, which would be a positive coupling. But if we're above that optimum, at which daisy growth is most rapid, further increases in temperature will lead to decreases in daisy growth, and we'll have a negative coupling. So the direction of this particular coupling depends on what the existing temperature already is. This will become more clear in a moment. So let's pick this diagram apart a little bit more, and now we're going to move into a depiction of phase diagrams, which is a plot of the two of the state variables of a system against each other. So if we're thinking about this coupling from daisy cover to surface temperature, we know that daisies have a high albedo, and that an increase in daisy coverage is going to reflect more incoming solar energy and lead to a decrease in temperature. And so we could draw a line on this diagram where high daisy coverages are associated with low surface temperature. So we'll start out over here, high daisy coverage, low surface temperature, and low daisy coverage, which is associated with a darker planet, is going to have a higher surface temperature. So we could draw a line that looks like this. Okay? So just this text here is assigning values to albedo. Albedo does vary between 0 and 1. A value of 1 is a high albedo, the highest possible albedo, when all incoming solar energy is reflected, whereas an albedo of 0 is no reflection of solar energy and complete absorption. So let's now consider this more complicated response of daisies to surface temperature. So I've already told you that this exhibits an optimum. So daisy coverage is highest at intermediate surface temperatures. We could put a point right there. And because that's a maximum, we could just draw a simple hump-shaped curve here. I'll draw it to look a little bit like a parabola. So here's our optimum temperature for daisy growth. And we've already discussed how the sign of the coupling changes around that optimum temperature. But let's go ahead and put this on the diagram. So when we're over here on this side of the optimum, temperatures are a little cooler than daisies would like it to be. So an increase in temperature leads to an increase in daisy coverage, and we have a positive coupling. So on this side, we have, I'm just going to represent these as a box with T for temperature and then a flower over here. So we have an increase in temperature leading to an increase in daisy coverage, which is a positive coupling. In contrast, over here, temperatures are a little warmer than daisies like it, and further increases in temperature lead to further decreases in daisy coverage. So over here, we have just the opposite. We have a negative coupling from temperature to daisy growth. Okay. So moving on, let's consider what happens now when we combine the two different relationships. So let's talk about that coupling that we were just now representing on the previous slide. So this is the coupling from temperature to daisies. And then we had our coupling from daisies, from daisy coverage to temperature. And that was a straight line that looked a little bit like this. Let me go ahead and show that in a different color just so we don't get these two things confused. Okay. So this is from daisies to temperature. Okay. So now our phase diagram consists of two lines, meaning that it represents a feedback process. As you might guess, there's something special that happens where these two lines intersect. So we're just going to highlight those intersections, and we're going to call this P1 and P2. Okay. We'll come back to this in a moment. But I just wanted to highlight on the next slide that these curves do intersect at P1 and P2. And the thing that's special about P1 and P2 is that these are our equilibrium states. They're the states that satisfy the relationships of both couplings. So the system must occupy one of those two states at equilibrium. So if we go to this diagram, you'll see that the system can't stay over here where the tip of my arrow is for very long because these two lines say both that daisy coverage should be way down here and way up here, which isn't the case. So the system can only exist where these two lines intersect. And in the next video, we'll tell you how to evaluate which one of these is a stable equilibrium and which one is an unstable equilibrium.